This video is brought to you by mywayteaching.com.
In this part, we are going to study about potential energy of a system of charges. Okay. Consider first the simple case of two charges Q1 and Q2. Okay, with position vector R1 and R2. As you can see in this figure, you just consider two charges Q1 and Q2 with position vectors R1 and R2 relative to some origin. And let us calculate the work done in building up this configuration. This means we consider the charges Q1 and Q2 initially at infinity, and then we'll determine the work done by an external agency to bring the charges from infinity to the point under consideration. Okay, which means to the given locations. Suppose first the charge Q1. Q1 is brought from infinity to the point R1. There is no external field in that particular case because that's the first step we are bringing against which work needs to be done. There is no any other force which is going to oppose that, isn't it? So in that case, work done in bringing Q1 from infinity to R1 is 0 because no force is there to or we can say to avoid that. That is the first charge we are bringing, so there is no need to do any work in that case. This charge produces a potential in space which is given by, in the first case, V1 is equal to 1 by 4 pi epsilon naught Q1 by R1p, where R1p is the distance of a point P in space from the location of Q1. From the definition of potential, work done in bringing charge Q2 from infinity to point R2 is Q2 times the potential at R2 due to Q1. So work done on Q2 is given by one by 4 pi epsilon naught Q1 Q2 by R12. So where R12 is the distance between points 1 and 2. Since electrostatic force is conservative, this work gets stored in the form of potential energy of the system. Thus, the potential energy of a system of two charges Q1 and Q2 is given by the equation, that is U is equal to 1 by 4 pi epsilon naught Q1 Q2 by R12. Okay, if Q2 was brought first to its present location and if Q1 is brought later, then the potential energy U would be same. The potential energy expression is unaltered whatever the way the charges are brought to the specified location. Okay, because of path independence of work for electrostatic force. And this equation is true for any sign of Q1 and Q2 if both Q1 and Q2 are greater than 0. Potential energy is positive. For like charges, electrostatic force is repulsive and a positive amount of work is needed to be done against this force in order to bring that charge from infinity to a finite distance apart. For unlike charges, the electrostatic force is attractive. In that case, a positive amount of work is needed against this force in order to take the charges from the given location to infinity. In other words, we can say a negative amount of work is needed for the reverse path, that is from infinity to present location, so that the potential energy is negative in that particular case. And we can generalize this equation for any number of point charges. So let us calculate the potential energy of a system of three charges. Okay, if you consider a system of three charges, Q1, Q2 and Q3, okay, which are located at R1, R2, R3. So first, to bring Q1 from infinity to R1, no work is required. In that case, isn't it, potential energy is 0. When we bring Q2 from infinity to R2, in that case, the work done is given by Q2 1 by 4 pi epsilon naught Q1 Q2 by R12. The charges Q1 and Q2 produce a potential which any point P is given by V1 2 is equal to 1 by 4 pi epsilon naught Q1 by R1P plus Q2 by R2P, isn't it? So work done next in bringing Q3 from infinity to point R3 is Q3 times V12 at R3. So that expression is given by, in bringing Q3 1 by 4 pi epsilon naught Q1 Q3 by R13 plus Q2 Q3 by R23. Okay, the total work done in assembling the charges at the given locations is obtained by adding the work done in different steps, isn't it? So we get the total work done equation as, by adding both the steps, 1 by 4 pi epsilon naught Q1 Q2 by R12 plus Q1 Q3 by R13 plus Q2 Q3 by R23. Because of the conservative nature of this electrostatic force, the final expression for U is independent of the manner in which the configuration is assembled. Okay, the potential energy is characteristic of the present state of configuration, not the way the state is achieved. How you bring, whether you bring Q1 first, Q2 first, Q3, that doesn't matter. Whichever the charge you bring first, the expression remains the same. Okay. Now, let us see a simple problem. 4 charges are arranged at the corners of a square ABCD of side D as shown in the figure. Find the work required to put together this arrangement. First one. Second is, a charge Q0 is brought to the center E of the square. The 4 charges being held fixed at its corner, how much extra work is needed to do this? This is the problem. Work done as well as for the charge Q, which is Q0. Let us find the solution for this question. Okay. For the first question, potential, total potential. See, work done depends on the final arrangement of the charges and not on how they are put together. This is clear, right? So we calculate work needed for one way of putting the charges at A, B, C, D. Suppose first the charge plus Q is brought to A and then charges minus Q, plus Q and minus Q are brought at B, C, D respectively. So the total work needed can be calculated in steps, isn't it? So the first step is in that. So we are work needed to bring a charge Q to A where no charge is present. So first it is obviously 0. When we bring charge Q to the point A, there is no external force here. So that is 0. The potential in that case is 0. And the second case, when we bring charge minus Q to point B. So now plus Q is at point A. This is given by charge at B into electrostatic potential at B due to plus Q charge at A. So charge at B is given by minus Q and electrostatic potential due to charge at A is given by Q by 4 pi epsilon naught into D, which is equal to minus Q square 4 pi epsilon naught into D. This is the second part. And the third part, now we are bringing charge plus Q at C, but already we have charge minus Q and plus Q at A and B, isn't it? So again now charge at C and electrostatic potential due to charge at B as well as charge at A. We should consider both. So when we consider the electrostatic potential due to charge at A, at that time that is given by plus Q 4 pi epsilon naught, distance of this points from A to C, that is given by D root 2. If you apply hypothesis theorem, we'll get. And due to charge at B, the potential is given by minus Q 4 pi epsilon naught into D, isn't it? And if you take common minus Q square 4 pi epsilon naught into D, we get 1 minus 1 by root 2. Okay. This is the third part. And if you consider the fourth part now, in bringing charge minus Q at D, now the charge plus Q is at A, minus Q is at B and plus Q is at C, isn't it? So the charge at D into potential due to charge at A is given by Q by 4 pi epsilon naught into D, isn't it? The distance is D. Now potential due to the charge at B is given by minus Q 4 pi epsilon naught square root of 2 into D, because the distance from B to D is given by root 2 into D. And due to charge at C, the potential is given by Q by 4 pi epsilon into D. So if you take the common, then we get minus Q square 4 pi epsilon naught into D, 2 minus 1 by root 2. Okay, now we should add all the final results that we got in all 4 cases in order to get the total work done. So which is given by minus Q square 4 pi epsilon naught into D. First step 0, second step 1, Third step, 1 minus 1 by root 2 plus 2 minus 1 by root 2, isn't it? And if you simplify this, the total work done is given by this is the work done depends only on the arrangement of charges and not how they are assembled. So by definition, this is the total electrostatic energy of the charges. Okay. Now coming to the second part of the question where they are asking when the charge Q0 is placed at origin, the extra work necessary to bring a charge Q0 to point E when the four charges are at A, B, C and D is Q0 into electrostatic potential at E due to charges at A, B, C, D. The electrostatic potential at E is clearly zero since potential due to A and C is cancelled by that due to B and D. Two are positive and two are negative charges and they are all at the equal distance. So if you want to calculate the potential, the result will be zero. So no work is required to bring any charge to point E. Okay.